Hey everyone, welcome to homework 4.2. Today we looked a little bit more at some of our quadratic functions, and we're going to look at a couple problems that illustrate a few more examples. So, how many small squares are in step 10? Well, here, remember, we're looking for the pattern of squares, right? So here we have the step number squared, and then we have a plus 1 here. But notice here, we also have n, right, on both sides. But now we have plus 2 blocks. So what about when we look at this one here? Here we have n times n again, right? Step 3, 3 times 3 is 9. But then we're adding 3 blocks. Notice the number that we're adding matches the step number. So here the equation we're looking at is n squared plus n, because we're squaring the step number, and then we're adding the step number to it. So if we're looking at step 10, then it would be 10 squared plus 10, which is going to be 110. Here are two patterns of dots, pattern A and pattern B. How many dots will be there in step 4 of each pattern? So let's take a look. We start with 4, 8, 12. So here we can see that we're adding 4 each time. There's 0 here. So if we're adding 4 each time and we're starting with 0, this means that our pattern is 4 times n, right? So for it says step 4, then we would have 16 dots. Our second pattern, though, we have a square happening, and then we are adding, it looks like, 2 dots. Now, for this first one, then, for step 0, we don't have anything. We're squaring 0, right? 0 squared plus 2. And then we are adding the 2 dots to the bottom of each step. So for step 4 then, let's write an equation for this. This would be n squared plus 2. And so then we would, in step 4, have 4 squared plus 2, which is 18. Which pattern shows a quadratic relationship? This would be pattern B, because the step is squared, so it contains that squared term, and then you add 2. Whereas if we compare, pattern A is what we would call a linear pattern, because we are simply adding the number 4 each time. Number 11 says, here are descriptions for how 2 dot patterns are growing. So pattern A has 10 dots, and it grows by 3 dots at each additional step. Pattern B, the total number of dots can be expressed by this equation, where n is the step number. For each pattern, draw a diagram of step 0 to step 3. So 0, 1, 2, 3 for pattern A, and then 0, 1, 2, 3 for pattern B. So A and B. Pattern A says step 2 has 10 dots, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It grows by 3, so 3 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That means that before here we have 7. 1, 2, 3, 4, 5, 6, 7. And before here we would have 1, 2, 3, 4. Right, so our pattern here would be 4 plus 3n. So for this equation now, 2n squared plus 1, well, n squared, if it's 0, is 0 times 2 is 0 plus 1. This would only have 1 dot. 1 would be 1 squared is 1 times 2 is 2 plus 1 is 3 dots. 2 squared is 4 times 2 is 8 plus 1 is 9. And then 3 squared is 9 times 2 is 18 plus 1 is 19. Let me make sure I did that right. 3 squared, 9 times 2 is 18. Yeah, 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All right. So in this case, we're squaring n, then multiplying it times 2, and then adding 1. All right. So let's think about where you might see that in this pattern. If I, just so you can see here, right? Squaring 1, then multiplying it by 2, so now we have 2, and then adding an additional 1 here. That's where we get these 3. All right, so 2 squared is 4, so squaring, and then multiplying it times 2 to give us 8, and then adding 1, right? So if we look at this as 1, 2, 3, 4, then we're multiplying it times 2, so now we have another 4. That's 8, and then we add 1. Okay, so just to show you how we got that here. 3 squared gives us this 9, and then we're going to multiply that times 2, so we'll have 18 plus an additional 1. All right, number 12. Each expression represents the total number of dots in a pattern where n represents the step number. Select all expressions that represent a quadratic relationship between the step number and the total number of dots. If you're stuck, sketch a few steps of each pattern. Now remember, we're looking for any place that we have a squared term. So A is a great one. B is linear. This is increasing by 2 each time. C is the same as n squared, so that demonstrates a quadratic function. N plus n is 2n. That's the same as B. It's also linear. N plus 2 is also linear. We have a y-intercept of 2, a slope of 1. And n divided by 2 is going to also be linear. It would be the same as 1/2 times n. Number 13. The function C gives the percentage of homes using only cell phone service X after 2004. Explain the meaning of each statement. So this is a review of functions. So the input is 10 years after 2004. So in 2014, there are 35% of homes using only cell phones. C of X is X years after 2004, there are 10% of homes using only cell phones. How is C of 10 different from C of X equals 10? So in here, C of 10 means number of years since 2004 versus C of X equals 10 gives us the percent after a certain number of years. And so in this first case, this 10 is the input, but in the second case, this 10 is the output. Number 14, here are some lengths, widths, and areas of a garden whose perimeter is 40 feet. Complete the table with the missing measurements. What lengths and width do you think would produce the greatest, largest possible area? So keep in mind again that that square creates the largest possible area for us. If the total perimeter is 40, let's draw that, right? The total perimeter has to equal 40. That means the length and the width have to equal 20. All right, which is half of 40. So our length and our width then could be 10. This would be 100. 8 times 12 is 96. If we have 12 as a length, we have 8 as the width. So that would be the inverse of this, right? Also 96. 14 means it's 6. 14 and 6 there is 60. Oh, no, sorry, 14 and 6. So 6 times 14, 24, carry the 2 is 84. Sorry about that, there we go. 84. And then 16 and 4 gives us 64. So here, if we look at this, seeing this, the highest point is where the length and the width, the highest area rather, is where we see the length and the width being 10, where they're equal to each other, and that makes sense because that would be the square. So 10 times 10 is the largest area. Any decrease in length or width would cause the area to also shrink, and then therefore not give us the greatest area. Number 15, a bacteria population is 10,000 when it was first measured, and then it doubles each day. Okay, so looking at this immediately, I see this is a review of our exponential functions, so we don't forget those. Use the information to complete the table. Which is the first day after the population was originally measured that the bacteria population is more than 1 million. All right, so let's write our equation. We have 10,000. It doubles each day, so we're doing times 2 to the power of x. Remember, if that x is in the exponent, it is an exponential function, not a quadratic one. Even though there's an exponent in a quadratic function, the exponent in a quadratic function contains a 2, a square. Okay, so at 0 days, it is 10,000. Then it is going to double, and it's going to keep doubling every time. Now notice here that we skipped to 5, so you do have to be careful here, and that's why I created my equation, because then I can put that in my calculator. So let's pull up the calculator. So in my calculator, I can go ahead and put this in here as 10,000. Oops, excuse me. Oh, I keep doing that. This, my numbers are kind of moved up. There we go. 10,000 times 2 to the power of x. And we can do second table to find out our value. So at 5, it would be 320,000. And then at 10, we're looking at 1.02 e to the 7th power. Now the e to the 7th power means we're moving those decimals over 7 times. So 102, moving the decimal over 3 times, or 7 times. 1, 2, 3, 4, 5, 6, 7. Okay, so 10,200,000. And so then our population in terms of D, using our equation, would be 10,000 to the times 2 to the power of D. All right, and so the question asks then, what is the first day after the population was originally measured that the bacteria population is more than 1 million? Well, let's look and see where it gets to the 1 million point. It appears that when we get to the 7th day, we are going from 640,000 to 1.2 million. All right, and so that would be between days 6 and 7. So on day 7, that's when the bacteria population is more than 1 million. All right, this last part is graphing inequalities, so you cannot forget about these. Now, remember to graph an inequality, we want to make it look like y equals mx plus b, or our slope-intercept form. So 7x minus 3y is greater than or equal to 21. I'm going to subtract 7x from both sides. We have negative 3y is greater than or equal to negative 7x plus 21. Remember, I can rewrite 21 minus 7x as negative 7x plus 21 because of our commutative property. And then I'm going to divide both sides by this negative 3. Now remember two things. When we divide by a negative with an inequality, we have to flip this sign. So now we have y is less than or equal to, and we also have a negative divided by a negative, which is a positive 7/3 x, a positive divided by a negative, which is divided by, or a minus, 21 divided by negative 3 is negative 7. It is important also to remember that when we divide on one side, we have to divide all the terms on the other side by the same number. So now I have a slope and a y-intercept. My y-intercept is negative 7, so I'm going to start here. My slope is up 7 over 3. So 1, 2, 3, 4, 5, 6, 7 over 1, 2, 3. Up 1, 2, 3, 4, 5, 6, 7 over 1, 2, 3. Okay. And then I can go ahead and I can use my ruler. Let's kind of get that in there. Line up my points the best that I can. and draw my line there. All right, so now I have the line, and I've made it a solid line because I have a less than or equal to sign, and I need to decide which side to shade. So let's test a point 0, 0. If I test the point 0, 0 and I plug in 0 for y and x, I would get 0 is less than or equal to -7. Well, that is not true. That does not work. Therefore, that tells me I need to shade the other side of my graph. And if I were to test a point on this side, let's say 6, 0, that would work. So if 0 is less than or equal to, this would be 6 times 7 is 42, divided by 3 is 14, minus 7 equals 7. So 0 is less than 7. That does work, and so we know we've shaded the correct side. Okay, so if you've forgotten about how, one, to put things into slope-intercept form, make sure to review that. And if you've forgotten how to know which side to shade, this is a good opportunity for you to review that as well. Again, we also see that we have a place where we can see our slope, we can see our y-intercept, and those things are helpful as well. And I do want to name one other way that we can plot these points is to substitute 0 for x and see what we get for y. If we would do that, we would get 0, -7, which tells us our y-intercept, which we have right down here, right? And then if I were to substitute 0 for 3, I would get x equals, sorry, not 0 for 3. If I substitute 0 here for the y, then I would get x equals 3. And we see that right here, where we have 3, 0 as our x-intercept along the x-axis. All right, that is it for your homework tonight. Super short and sweet. Please make sure to go ahead and fill out the code word if you listen to the whole thing. Your code word will be refresco, and if you look that up and you spell it correctly, then I'll give you extra points. Refresco. It's a Spanish word. Tell me what it means. All right, happy homeworking and see you tomorrow.